I want to tell you about a number I never got to see resolved, and then about a telescope launched decades after my death that has managed to make the problem surrounding that number considerably stranger than anyone expected. The number is called the Hubble constant, named for Edwin Hubble, an astronomer I knew personally, whose observations in the late 1920s first demonstrated something that reshaped how every physicist of my generation understood the universe. Hubble showed that distant galaxies are receding from us, and that the further away a galaxy sits, the faster it appears to be moving away. This wasn't galaxies simply flying apart through space in the ordinary sense. It was space itself expanding, carrying galaxies along with it. A discovery that transformed the universe from something static and eternal, the way most physicists, including Einstein himself, had initially assumed it must be, into something with a history, a beginning, and an ongoing story of expansion that continues even now. The Hubble constant is simply the number that describes how fast that expansion is happening at the present moment. How much faster a galaxy appears to recede for every additional unit of distance separating it from us. Get this number right, and you can work backward to calculate the age of the universe itself. Extrapolate forward to understand its ultimate fate, and calibrate essentially every other measurement in cosmology that depends on distance and time. I want to be honest that pinning this number down precisely occupied astronomers for most of the 20th century, and it remained stubbornly imprecise for decades, with different research groups using different techniques, arriving at values that disagreed with each other by factors of 2 or more well into the 1990s. This wasn't considered a crisis exactly during my own working life. It was simply understood as an unsolved measurement problem, the kind of thing astronomers expected better instruments would eventually resolve. What I want to walk you through now is what happened once those better instruments actually arrived, because the resolution nobody expected was that improving our measurement precision didn't converge the disagreement toward a single answer. It made the disagreement sharper, more statistically certain, and considerably harder to explain away as ordinary measurement error. By the early 21st century, astronomers had 2 genuinely independent methods for measuring the Hubble constant, each relying on completely different physics, and each individually achieving a level of precision that would have seemed extraordinary to anyone working in my era. The first method works in what astronomers call the local universe, measuring distances to relatively nearby galaxies using objects called Cepheid variable stars, a class of star whose brightness pulsates in a way directly tied to its true luminosity, discovered originally by Henrietta Leavitt in the early 20th century. Because you can determine a Cepheid's true brightness from its pulsation period, comparing that true brightness to how bright it actually appears from Earth tells you with real precision how far away it is. Chain enough of these distance measurements together, out to galaxies whose recession velocities you can also measure directly. And you get a direct empirical value for the Hubble constant, built entirely from observations of the universe as it exists, relatively nearby and relatively recently, cosmologically speaking. The second method works entirely differently, reaching back not to nearby stars, but to the earliest light in the observable universe, the cosmic microwave background. The faint afterglow of radiation released roughly 380,000 years after the Big Bang, when the universe first cooled enough for light to travel freely rather than being constantly scattered by a hot, dense plasma. The European Space Agency's Planck satellite measured this ancient radiation with extraordinary precision, mapping tiny temperature variations across the entire sky. From those measurements, combined with our best theoretical model of how the universe has evolved since that early moment, a model called lambda CDM, incorporating dark matter and dark energy as its central ingredients, cosmologists can calculate what the Hubble constant should be today, as a prediction derived from the physics of the early universe rather than a direct local measurement. Here is the problem that has occupied cosmologists for the past decade and a half, and that James Webb has now made considerably harder to dismiss. These two methods disagree. The local direct measurement using Cepheid variables consistently produces a value around 73 kilometers per second per megaparsec. The early universe prediction, derived from Planck's measurements of the cosmic microwave background, consistently produces a value closer to 67. That's roughly a 9% discrepancy, and I want to be clear about why a 9% gap in this specific context is considered so troubling. Both measurements individually come with error bars far smaller than the size of the gap between them. This isn't two imprecise measurements that happen to overlap once you account for their uncertainty. It's two increasingly precise measurements that stubbornly refuse to agree, no matter how much the precision of each individual method improves. For years, the leading, most conservative explanation was that one of the two measurement techniques contained some subtle, undiscovered systematic error, some overlooked source of bias in how Cepheid distances were calibrated, perhaps, that was quietly skewing the local measurement upward. This was, I think, the explanation most cosmologists genuinely hoped would turn out to be correct, because a measurement error is a solvable problem, one that better instruments and more careful technique can eventually fix, without requiring any revision to our fundamental understanding of the universe's physics. This is where James Webb enters the story, and where the hope for a simple measurement error explanation has become considerably harder to sustain. Webb's infrared instruments are dramatically more sensitive and precise than the previous generation of space telescopes, and one of the specific tasks astronomers assigned to it, starting shortly after it became operational in 2022, was revisiting the Cepheid distance measurements that underpin the local Hubble constant calculation, to check directly whether Hubble Space Telescope's earlier measurements had been compromised by exactly the kind of systematic error cosmologists hoped might resolve the tension. The team, led by astronomer Adam Riess, whose earlier work on distant supernovae had helped establish the existence of dark energy in the first place, used Webb specifically to check whether a phenomenon called Cepheid blending, where a target Cepheid star's measured brightness gets contaminated by light from other unrelated stars crowded into the same small patch of sky, artificially skewing the brightness measurement and therefore the calculated distance, might explain the discrepancy. Webb's superior resolution allowed astronomers to separate individual stars far more precisely than Hubble ever could, directly testing whether blending had been corrupting the earlier measurements. The result, published in 2024, confirmed that the earlier Hubble measurements had been correct all along. Webb's more precise observations agreed with Hubble's original Cepheid distance measurements, closing off the most widely hoped for explanation for the discrepancy. As Riess put it directly, once measurement error had been effectively ruled out as the culprit, what remained was the considerably more unsettling possibility that we have genuinely misunderstood something fundamental about how the universe works. I want to sit with that conclusion for a moment, because I think it's worth being precise about what it actually implies. It doesn't mean the Big Bang didn't happen or that general relativity is simply wrong. The theoretical framework I spent years of my own career working within remains extraordinarily well tested in nearly every context we've been able to check it against. What it suggests instead is that the specific model cosmologists use to describe the universe's contents and evolution, the lambda CDM model built around dark matter and dark energy, may be missing some ingredient, some piece of physics not currently accounted for, that would reconcile the early universe prediction with the local direct measurement. There have been numerous theoretical proposals attempting to explain the gap, and I want to walk through a few of the more seriously considered ones, while being honest that none has yet achieved anything like consensus support. Some cosmologists have proposed modifications to dark energy itself. Perhaps its density or behavior isn't constant over cosmic time the way the simplest version of lambda CDM assumes, but instead evolves in some way that would shift the calculated expansion rate. Others have proposed the existence of additional exotic forms of radiation in the early universe, sometimes called dark radiation, that would have influenced the physics of the early universe in ways the standard model doesn't currently include, altering the predicted value of the Hubble constant derived from the cosmic microwave background without requiring any change to the local measurements at all. Still, others have proposed a period of accelerated expansion occurring earlier in cosmic history than the dark energy-driven acceleration we currently observe, sometimes called early dark energy, which would specifically address the discrepancy by altering physics in the crucial window before the cosmic microwave background was released, without necessarily requiring changes to physics in the more recent universe that local measurements are sensitive to. I find myself genuinely uncertain reading through these proposals, which, if any, will eventually prove correct. And I don't think that uncertainty reflects poorly on the physicists working on this problem. This is exactly the situation physics finds itself in when a well-established theoretical framework runs into a genuine, confirmed empirical anomaly it can't currently accommodate. A situation I have some personal familiarity with, having spent real time in 1939 staring at equations describing gravitational collapse that led somewhere my framework at the time couldn't fully explain either. But the Hubble tension isn't the only anomaly Webb has uncovered that troubles cosmologists, and I think the second problem is, in some ways, even more directly unsettling to the standard picture of how the universe assembled itself. This concerns galaxies, specifically galaxies that Webb has observed existing far earlier in cosmic history and in a far more mature, fully formed state than the standard model of galaxy formation predicted should be possible. One of the specific capabilities that makes Webb such a transformative instrument is its ability to observe extremely distant, extremely early objects in the universe. Because looking at greater distances is equivalent to looking further back in time. Light from very distant galaxies has been traveling toward us for billions of years, meaning we're seeing those galaxies not as they exist today, but as they existed in the deep past shortly after their formation. Webb's infrared sensitivity allows it to detect galaxies existing within the first few 100 million years after the Big Bang, a period cosmologists refer to as the early universe, or in some context, the cosmic dark ages, transitioning into what's called the epoch of reionization. The standard model of galaxy formation predicts that galaxies at this early stage of cosmic history should be small, relatively disorganized, and chemically primitive, composed almost entirely of hydrogen and helium, the two elements produced directly by the Big Bang itself, since heavier elements need to be synthesized inside stars and then distributed into surrounding gas through supernova explosions, a process that takes multiple generations of stars, and therefore considerable cosmic time to meaningfully enrich the composition of galaxies. What Webb has actually found in several specific observations that have generated considerable discussion and, in some cases, genuine concern among cosmologists, is different from this prediction in ways that are difficult to easily dismiss. Some of the earliest galaxies Webb has detected appear to be considerably larger, more massive, and more structurally organized than the standard model predicted should be achievable so soon after the Big Bang. One particularly striking example is a galaxy catalogued as month-over-month Z14, observed existing when the universe was only around 280 million years old, a period so early in cosmic history that, under the standard model's predictions, galaxies should barely have had time to begin assembling at all, let alone to have already undergone the multiple generations of star formation and death required to meaningfully enrich their gas with heavier elements. Spectroscopic measurements of this galaxy's light revealed an unexpectedly high abundance of nitrogen and carbon, elements that require substantial prior stellar activity to produce in any meaningful quantity. Present in a galaxy existing at a point in cosmic history where the standard model suggested there simply hadn't been enough time for that stellar activity to have occurred. I want to be careful here because I think this specific finding and others like it get presented with varying degrees of accuracy and alarm, depending on the source. And I want to give you the most honest version of where the scientific discussion actually stands. This is not, at this stage, a confirmed refutation of the standard cosmological model in the way some more sensational discussions of it suggest. Several explanations remain under active consideration that wouldn't require abandoning the core framework of the Big Bang or the standard timeline of cosmic structure formation. Some researchers have proposed that early star formation may simply have proceeded faster and more efficiently than standard models assumed, perhaps because early galaxies contained unusually massive, extremely luminous stars that lived and died more quickly, enriching their surrounding gas with heavier elements on a faster timescale than typically modeled. Others have raised the possibility that at least some of these apparently very massive early galaxies may be systematically overestimated in mass due to uncertainties in how astronomers convert observed brightness and color into estimates of stellar mass for objects this distant and difficult to observe in detail. But I also want to be honest that these explanations, while plausible, have not yet fully resolved the tension to the satisfaction of the entire cosmological community. And the number of individual observations posing this kind of challenge has grown steadily since Webb became operational, rather than shrinking as astronomers gathered more data, which is generally not the pattern you'd expect if the issue were simply a matter of a few unusual, easily explained outliers. I think what makes both of these anomalies, the Hubble Tension and the unexpectedly mature early galaxies, genuinely significant rather than simply interesting footnotes in an otherwise settled field, is that they're pointing toward potential gaps in the same broad theoretical structure from two largely independent directions. The Hubble tension emerges from precise measurements of cosmic expansion rates. The early galaxy problem emerges from direct observations of how quickly structure assembled in the young universe. These are, in principle, separate lines of evidence using different instruments, different techniques, and different physical phenomena. The fact that both are producing results that sit uncomfortably against the predictions of the standard lambda CDM model at roughly the same historical moment as Webb's superior observational capabilities came online is at minimum a signal that cosmologists take seriously, even while remaining appropriately cautious, about declaring the standard model broken outright. I want to draw a comparison here to my own experience because I think it illuminates something true about how this kind of scientific uncertainty actually feels from the inside, rather than how it gets summarized after the fact. When Snyder and I worked through the mathematics of gravitational collapse in 1939 and arrived at a singularity our theory couldn't properly describe, we didn't conclude that general relativity itself was wrong. We concluded that our framework, applied in that specific extreme regime, was running into the edge of its own validity, a signal that something further needed to be understood, some additional physics incorporated before the picture could be made complete. It took decades and tools I never had access to during my own lifetime before that particular edge case was even partially resolved. I suspect something structurally similar is happening now with these cosmological anomalies, though I want to be honest that I can't tell you with any real confidence whether the eventual resolution will require modest adjustments to the existing lambda CDM framework or something closer to a genuine paradigm shift in how we understand dark energy, dark matter, or the early universe's physics. What I can tell you from having lived through one significant decades-long gap between an unresolved theoretical anomaly and its eventual clarification is that these periods of genuine confirmed tension between theory and observation are exactly the moments in physics where real foundational progress tends to eventually emerge. Not despite the discomfort of an unresolved anomaly, but often because of it. Because a confirmed discrepancy, this significant forces careful physicists to question assumptions that might otherwise have gone unexamined for much longer. The scientists working on this problem now have tools at their disposal I could genuinely never have imagined during my own working life, not just Webb itself, but upcoming instruments like the European Space Agency's Euclid mission, designed specifically to provide an independent third perspective on the Hubble tension through entirely different observational methods, with its primary results expected in 2026. Ground-based projects like the Dark Energy Spectroscopic Instrument are simultaneously gathering enormous quantities of data on the large scale, structure of the universe, providing yet another independent check on the same underlying questions. I find myself genuinely curious, in a way I don't often let myself express, about questions I'll never see resolved, about where this particular story eventually leads. Cosmology, more than almost any other field I ever worked adjacent to during my own career, is a discipline where the questions being asked are, in a very real sense, questions about the entire universe's structure and history, rather than questions confined to a single laboratory experiment or a single physical system. When a confirmed anomaly emerges at that scale and persists despite genuinely rigorous attempts to explain it away as measurement error, it suggests we may be standing at the edge of understanding something we didn't previously know we didn't understand. The exact position, I think, that the most interesting and consequential moments in the history of physics have always eventually occupied.